Welcome to The Explainer. You've probably used tools like ChatGPT, right? But have you ever stopped to wonder what's really under the hood? Well, today, we're diving into the revolutionary 2017 paper that is basically the blueprint for almost all modern AI. It's called Attention is All You Need, and it completely changed the game for how machines understand language.
So, to really get this, we've got to go back in time a bit. What was the big problem that the Google researchers were even trying to solve? Before AI could write code and poetry, there was this one fundamental bottleneck holding the entire field back.
Before 2017, the kings of language processing were these things called recurrent neural networks, or RNNs for short. For years, they were the state-of-the-art for things like machine translation. But they had this one major, critical weakness.
Here's how RNNs worked. They read sequentially, one word at a time. Imagine trying to read a giant novel, but you're only allowed to look at it through a tiny little pinhole. By the time you get to the last chapter, are you going to remember some specific detail from the first? Probably not. Well, that's exactly the problem RNNs had. And here's the kicker, the really crucial point from the paper. Because they had to process word by word, you couldn't throw a bunch of powerful computers at the problem all at once to speed things up. It created this massive bottleneck, making them incredibly slow to train and, as we said, prone to completely forgetting the context in long sentences.
Okay, so this slide just lays it all out perfectly. On the left, you've got the old way, slow, plodding along one word at a time, and pretty forgetful. And on the right, that's the dream. That was the goal. A model that could be trained super fast, in parallel, and actually grasp the full context of a sentence, no matter how long it was.
All right, so this is where it gets really interesting. The Google researchers looked at this whole sequential problem and did something pretty radical. Instead of trying to make small improvements, they just threw the whole idea out.
They asked this really simple but honestly profound question. What if, instead of reading word by word, a model could just see the entire sentence at once and decide for itself which words are most important to each other?
And that brings us to the core concept, the big idea, self-attention. So instead of that tiny pinhole, you're looking at the whole page. Your brain instantly connects the word it back to the noun it's referring to, even if that noun was 10 words earlier. Self-attention gives a model that exact same superpower.
This incredibly powerful idea of self-attention wasn't just a concept, it became the foundation for a totally new architecture for understanding language, the transformer. And here it is. This is the diagram that basically launched a revolution, the transformer. It's a model built not on that old, slow, sequential idea, but entirely on this new concept of self-attention. On the left, you have an encoder that reads and understands the input, and on the right, a decoder that generates the output.
Now let's look at the engine inside this thing, because it gets even cooler. It doesn't just use one self-attention mechanism. No, it uses what's called multi-head attention. The paper used 8 heads, so you can literally imagine it like having a team of 8 experts reading the sentence all at the same time. One might focus on grammar, another on semantic meaning, another on context. It's brilliant.
But wait a minute. If the model sees all the words at once, how does it know their original order? The dog chased the cat is very different from the cat chased the dog, right? Well, the authors solved this with a really clever mathematical trick called positional encodings. They add a unique signal to each word based on its position, which ensures the model never loses the original sequence of the sentence.
So the idea was super elegant, a beautiful concept. But the real question, the only one that really matters is, did it actually work? The proof, as always, is in the performance. And oh boy, did it work. Look at this table. On the industry standard English to German translation task, the transformer didn't just compete, it completely smashed the previous records, setting a new state-of-the-art with a score of 28.4. And just to be super clear, this was not a small improvement. In the world of machine translation, a jump of over 2 blue points is a massive leap forward. It signaled a major breakthrough.
And why was it so much faster to train? This table tells the whole story. For an old recurrent network, the path for information to travel between the first and last word grows with the sentence length. For the transformer's self-attention, the path length is constant. Any word can connect directly to any other word in a single step.
So the big takeaway is that the transformer wasn't only more accurate, it was also dramatically more efficient.
The big model set that new record after training for just 3.5 days, a fraction of the cost and time of the previous state-of-the-art models.
This incredible combination of top-tier performance and wild efficiency, well, it had implications far, far beyond just machine translation. It provided a whole new foundation for the field to build on.
I mean, the Transformer's legacy is just huge. Its parallel design was a perfect match for modern GPUs, which allowed for massive scaling. Its ability to understand long-range context was a total game-changer. It became the essential blueprint for nearly every large language model today, from BERT and T5 to the entire GPT family.
And this leaves us with a final thought. The Transformer proved that one radical idea, throwing out sequential processing, could change everything. It makes you wonder, what fundamental assumption are we all clinging to today that's holding back the next breakthrough in AI?